Good morning, everybody. Today we're going to be doing experiment number 5, which is measuring the specific heat of various metals. So the setup we're going to use basically looks like this, although we will separate these into two separate stands when we go into the laboratory. On the right side, we have a beaker in which we can heat our metal samples. So we're going to take first a sample of copper. This is our standard, which we'll practice with. And we'll be heating a sample of copper up to 100 degrees Celsius in the boiling water bath. And then we'll transfer that 100-degree copper into our calorimeter. So this calorimeter is basically just a couple of styrofoam cups with about 100 milliliters of water in it. We're going to measure the temperature of the water initially, and then we'll add the 100-degree metal sample to it, swirl it around for a minute or two. The temperature will rise, and we'll measure how much the temperature has increased, and from that we'll be able to determine how much energy actually flowed into the water. So whatever energy went into the water must have come from the copper. Now in the pre-lab that we'll be viewing in a couple of minutes, I'll take you through all of the calculations that you'll have to do. And then after that we'll go ahead and move on into the laboratory and carry out the actual experiment. So the first thing we'll be doing is heating our water bath up to 100 degrees Celsius. And then we're going to test a sample of copper twice. And this is just to make sure you've got the technique down. We know that the specific heat of copper is 0.38 joules per gram degree Celsius. So we're going to simply measure that in the lab and make sure that you're getting reasonably close to that. Then we're going to take an unknown metal sample and we're going to measure the specific heat of that by doing that twice as well. And then looking at the table of specific heats in the lab manual, you should be able to identify your unknown. So now I'd like you to go ahead and watch the pre-lab video that I prepared, and then we'll head on over into the lab and actually carry out the experiment so that you can record the data and then do your calculations and answer the questions. As we talked about in the introduction to the experiment, we're going to be using specific heats to determine the identity of an unknown element. So first of all, what exactly is specific heat? The definition is the amount of energy required to heat 1 gram of a substance by 1 degree Celsius. So if a substance has a specific heat of 1, then it would take 1 calorie to heat up 1 gram of that substance by 1 degree Celsius. Now we measure specific heats commonly in two different units, either in calories per gram degree Celsius or joules per gram degree Celsius. Joules is the official SI unit, but calories is very common as you see it on food items. It's the same calories we talk about with foods. So these are the specific heats of some common materials. Water, as many of the properties happen to be, has a value of 1. In fact, the calorie was defined that way. The original definition of the calorie was the amount of energy required to heat 1 gram of water by 1 degree Celsius. So we base everything in comparison to water. There's approximately 4 joules in a calorie, 4.18 to be specific. So the specific heat in joules is always 4.18 times higher than the corresponding specific heat in calories. We'll be using joules in the lab today. Water happens to have one of the highest specific heats of any substance. And you can recognize something with a high specific heat because it's a material that is very slow to change temperature. Water has a tendency to maintain its temperature. If you have a swimming pool, for example, when summer comes, it often takes a lot of hot days before the water in the pool warms up because water requires a lot of energy. It takes 1 calorie to increase the temperature of each gram of water by 1 degree. Sand, on the other hand, is about 1/5 of that. So a single calorie would heat up a gram of sand by about 5 degrees. For air, since its specific heat is about a fourth that of water, a calorie would heat up a gram of air by about 4 degrees. Now, metals, particularly very dense metals like gold, tend to have very low specific heats. Gold's specific heat is more than 30 times less than that of water, which means that gold will heat up 30 times faster than water. A single calorie of energy could heat up a gram of gold by almost 33 degrees. So 33 times faster than water. Now, if you've ever been to the beach in the summertime, you'll notice that the water can be nice and pleasant, but the sand is burning hot. And the reason is very simple. Sand has a low specific heat, which means it heats up readily. So when the sun hits the sand during the day, it raises the temperature of the sand high enough it can actually burn your feet. The water, however, stays at pretty much the same temperature. Water's very slow to change, so the sun doesn't affect it much during the course of a day. At night, when the sun goes down, the water stays the same temperature, but the sand cools off dramatically. So now the sand feels nice and cool. Let's take a look now at how we'll be calculating specific heats of metals in the lab today. The equation for calculating specific heat involves 4 variables. Q is the amount of heat energy involved, either being gained or lost by an object. M, of course, is the mass of the substance that's being heated or cooled. Delta T is the change in temperature of the substance, and S is the specific heat. So as long as you know any 3 of those variables, you can solve for the other ones. So to get the specific heat of a substance, we need to know these 3 things. We need to know how much the object weighs, how much its temperature changed, and how much energy was either gained or lost during that temperature change. So we can rearrange the equation very easily to solve for specific heat. This device is a calorimeter, and a calorimeter is what we use to measure Q, or the amount of heat energy. The calorimeter we're going to use today will not be nearly this fancy. When I was in college as a chemistry major, we used a calorimeter of this type. So basically the way it works is you put a sample inside this thing called a bomb. And it's called a bomb because it holds a lot of pressure. You pressurize it with lots of oxygen, and you put a combustible material in there, maybe an M&M, or a gummy bear, something that has a lot of calories in it. And you ignite it with these wires, it bursts into flame, all the heat is released, and the heat warms up the water in the calorimeter. We simply measure the temperature of the water before the ignition and after, and we determine how many degrees the temperature of the water increased. Because we know for every degree that the temperature increased, and for every gram of water in the calorimeter, that would require 1 calorie, or 4.18 joules. So it's relatively easy to determine the value of Q. We just need to know the mass of water in the calorimeter. We need to know the temperature change, delta T, which we get from the thermometer. And of course, the specific heat of water is given as either 1 calorie or 4.18 joules per gram degree Celsius. In the lab today, we're going to be using what's called a coffee cup calorimeter, because basically it consists mainly of 2 styrofoam cups. The key about your calorimeter is it needs to be well insulated. We want to make sure that heat can't get in or out of the calorimeter. Whatever heat we put in needs to stay in, and we can't let heat from the outside get in there. And styrofoam is a pretty good insulator, and 2 styrofoam cups provides even better insulation. But we still have the same basics. We have the water in the calorimeter, which will be measuring a temperature increase on that. and we have our thermometer to measure the temperature. Some coffee cup calorimeters have a little wire stirrer to mix the water around. Today we're just going to sort of swirl the cup gently. The key is just to make sure the water gets mixed evenly so the temperature is the same throughout. So what we'll be doing is we're going to heat up a sample of metal to 100 degrees Celsius in boiling water. So we know that the initial temperature of the metal is 100 Celsius. We will weigh the amount of water in the calorimeter, so we have the mass, and we will measure the initial temperature of the water in the calorimeter as our starting point. We will then put the metal in the calorimeter, swirl it around, and the temperature will rise. We have the two changes of temperature to concern ourselves with. One will be the change in temperature of the water from whatever the starting temperature is of the water up till what it ends at. And the metal, of course, will begin at 100 degrees and it will drop down to that final temperature. So there's a delta T for the water and a delta T for our metal sample. To do our calculations, we're going to look at two equations. The first equation is going to involve water. So the W subscripts here mean we're referring to the water. So we know the mass of water in the calorimeter because we weighed that. The change in temperature of the water we can determine by measuring the beginning and ending temperature of the water bath. And we know the specific heat of water is 1 calorie or 4.18 joules per gram degree Celsius. With those three values, we can calculate Q. Now, the amount of energy that entered the water is the same as the amount of energy that left the metal, because that's where all that energy came from. So Q for the water is the same as Q for the metal. We simply rearrange the equation to now solve for the specific heat of the metal. We'll take Q that we measured in our calorimeter. We'll weigh the sample of metal prior to putting it in the boiling water, and the change in temperature of the metal will simply be the 100-degree starting temperature minus whatever the final temperature was in the calorimeter. And using those values, we can then come up with a specific heat of the metal. And then in the lab, you'll be looking at a table of various unknown metals, and you will attempt to match the specific heat you've come up with the specific heat of one of those metals, and that should allow you to identify your unknown. Now let's take some hypothetical experimental data and see how the calculations will be done so that you guys can follow the same procedure with the actual data from the experiment. So we have our styrofoam cup calorimeter with a mass of water that we've measured and our initial temperature. We weigh a sample of our unknown metal and then place it in the boiling water bath and heat it for several minutes until we're sure it's at 100 degrees Celsius. Then we place the metal into the calorimeter. After a couple of minutes, the temperature of the calorimeter water has risen from the 19.8 degrees we started with to 23.3. So let's see how we can use this information to determine the specific heat of our unknown metal and then identify the metal. We'll go back to our original equation. The first thing we need to do is calculate Q for the water. So we have the mass of the water provided, the change in temperature of the water from 19.8 to 23.3, and of course specific heat of water will use 4.18 joules per gram degree Celsius. So we can plug those numbers in, multiply them together, and we end up with a value of Q of 1486 joules. We won't worry about rounding this off yet because we're going to use this number in the next calculation. Now we're ready to take a look at the metal. We have our rearranged equation where we're now solving for specific heat. So we can still use the Q value that we obtained from the calorimeter. Now we want to use the mass of the metal, which is the 88.24 grams, and the change in the temperature of the metal will be different because the metal went from 100 degrees down to 23.3 degrees. So that delta T will be much larger. We'll go ahead and plug in those three values, and we come up with a specific heat of about 0.22 joules per gram degree Celsius. Let's see if we can use that information to figure out what our unknown metal is. So the way we can do that is we'll pull out our table from the lab book, and this lists a number of different metals that your unknown could potentially be. If we take a look at these specific heats, it looks like it could definitely be tin, because tin happens to have the exact same specific heat that we came up with. However, we need to keep in mind that these numbers are not exact. The rule of thumb is it'll be 0.22 plus or minus 0.01. So it could be as high as 0.23 or as low as 0.21. And that means that our unknown might also be silver. In this particular case, you could not conclusively determine the identity of your unknown. We would actually need some additional information. Could you come up with any ideas of what piece of additional information might allow us to make the final determination? Well, if you think back to the very first experiment we did this semester, the density lab, if we were to calculate the densities of these metals the same way we did back in experiment number 1, we would easily be able to determine which of these two metals our unknown was. By comparing the densities and the specific heats, it would be easy to determine exactly what our unknown is. So at this point, let's go ahead and move on over into the lab and collect some actual experimental data. I'll be, of course, carrying out the experiment, but I'll expect you to be recording the data from the videos that we take, and then you can use that data to calculate the specific heat of your unknown metal and then identify that metal. And then finally, answer the questions at the end of the lab. So let's go ahead and get started. The first thing we need to do is to set up our water bath and heat it up so that we can use it to heat our metals. So let's fire up the Bunsen burner. Let that water begin to heat. We'll let that get up to boiling, and while we do that, we'll go ahead and weigh out our first sample of copper, and then we can place it in the water and let it reach 100 degrees. While the water bath is coming up to boiling, let's go ahead and prepare our copper. We have two different options for the copper. We have copper rod, and we also have copper shot. We'll probably do one of each of those. The copper rod can be weighed directly, but the copper shot needs to be weighed in a container. So we'll use a test tube to hold the copper shot when we're going to heat that in the boiling water. The copper rod can be heated directly in the water. So for our first trial, let's weigh out this copper rod and record that value as the mass of the metal, and then we can go ahead and place that in the boiling water bath and heat it up to 100 degrees. It looks like our water has reached the boiling point, so let's go ahead and take that copper rod and place it in the boiling water, and we're going to let it heat up for several minutes. We want to make sure it reaches 100 degrees Celsius. So while that heats up, let's go ahead and set up our calorimeter. All right, while the copper is heating up over in the boiling water, let's prepare the calorimeter. First, we'll need to weigh the empty cups and record that mass. And now we'll add about 100 grams of deionized water. It doesn't have to be exactly 100 grams, as long as it's about that much. So we'll record the mass of that. We can subtract the two, and that will give us the mass of water in our calorimeter. This is our basic calorimeter setup. It has the two styrofoam cups nested for better insulation, a thermometer mounted in it, and a cardboard cover to help insulate the surface. Once we put the metal in, we'll lower the cardboard cover and swirl it around. But before that, we'll need to determine the initial temperature. So we'll record the temperature of the water at present, and then after the metal has been placed and the water is allowed to warm up, we'll measure our final temperature. This is the thermometer in the calorimeter prior to adding the hot metal. So record the temperature in your lab book. The metal's been in the calorimeter now for several minutes, and it looks like the temperature has stabilized. So take a reading on the thermometer now and record that, and then you can calculate the change in temperature for the metal and for the water. All right, this time let's try a sample of copper that's copper shot. So this will have to weigh out in our beaker. So record the mass of the empty beaker, and then we'll add a sample of our copper shot, and we'll be able to get a comparison then of whether there's a difference between the single piece of copper or the copper shot. So record this second mass as well, and then from that you can calculate the mass of copper in trial 2. Now we'll place the copper into a test tube and then immerse that in the boiling water bath. We'll let that heat for at least 5 minutes to make sure the copper's reached 100 degrees Celsius, and then transfer it to the calorimeter. While the copper shot is heating up in the boiling water bath, let's go ahead and prepare the calorimeter for trial 2. First, we'll need to weigh the empty styrofoam cups and record that mass. And then we'll add approximately 100 grams of deionized water, and then record that mass, and then subtracting those two will give us the mass of water for the second trial with the copper shot. Go ahead and record the temperature in the calorimeter initially before we add the copper shot. The copper shot was placed in the calorimeter. We swirled the water around and let it rise and level off. It's been a couple of minutes and it appears that it has reached its maximum. So go ahead and record that as the final temperature. Now let's go ahead and test an unknown sample. Since this is also a metal shot, we're going to have to measure it in a beaker. So let's first get the mass of our empty beaker and record that. And then we'll go ahead and add a sample of our metal. We'll try to get just about the right amount to fill the test tube, but not make it higher than the water level. That should be good. So record that final mass of the metal and the beaker, and then we can subtract the mass of the beaker to get our metal sample's mass. Let's go ahead and move that over into the boiling water bath. Now we place the first sample of our unknown metal into the boiling water bath. We'll let that boil for several minutes to make sure it's reached 100 degrees Celsius, and then we can transfer that to the calorimeter. While our first sample of unknown is heating up in the water bath, let's prepare the calorimeter. First, we'll weigh the two empty styrofoam cups and record that mass. And then we'll add approximately 100 grams of deionized water. And then go ahead and record that second mass. We can subtract the two, and that will give us the mass of the water for the first unknown trial. Before we add the sample of unknown to our calorimeter, let's go ahead and record the initial temperature of the water in the calorimeter. Our first sample of unknown has been in the calorimeter for a couple of minutes. The temperature seems to have leveled off.
So go ahead and record that as your final temperature. With any analysis of an unknown, we always like to repeat our results to make sure that they are consistent. So let's do a second trial. First, we'll weigh our empty beaker and record the mass. And then we can measure out a second sample of our unknown. All right, that looks like a good amount. So go ahead and record that mass, and then we will transfer our metal sample into the boiling water bath. Let's go ahead and heat our second sample of unknown for about 5 minutes in the boiling water bath to make sure that it reaches 100 degrees Celsius, and then we can go ahead and transfer that into the calorimeter. The second sample of unknown is now heating up in the boiling water bath, so let's prepare our calorimeter. As always, we'll first weigh the 2 empty styrofoam cups and record the mass. And then we'll add about 100 grams of deionized water. And go ahead and record that second mass, and then from that we can calculate the grams of water in the calorimeter. Before we add the second sample of unknown to the calorimeter, let's get the initial water temperature. The second sample's been in the calorimeter for a couple of minutes. The temperature rose up and appears to level off, so now you can go ahead and take a reading for T2. Now that we've finished obtaining all of our experimental data for the lab, there are just a few remaining tasks you need to accomplish before you can submit your work. The first thing you need to do is to calculate the specific heat of the copper in both trials, and then compare your value to the values in the table of known substances. Ideally, the value you obtain for copper will be close to the known value in the table. Second, you'll need to determine the specific heat of your unknown in each trial, and then compare your experimental values to those in the table, and you should be able to identify your unknown from that. And then finally, there are a series of questions at the end of the experiment, so you'll need to answer those, and once that's done, you will be ready to submit the lab.